Thank you, Court. So first let me thank my colleagues. So I'm going to show a sub-sample of some of my work over the last 10 years or so. And these are some of my colleagues who have helped me, who have been in my research group at one point or another. So I'm going to start by motivating CIS model physics. And I believe some of you may have seen this plot. Okay, right, jolly good. Well, carry on doing that, because you may not want to hear what I'm about to say next. So here we show September sea ice extent versus time, and well, it's been decreasing in the Arctic. Okay. So here where we may have a slight risk of dissension. So climate models have projected out the sea ice reduction over the coming decades. The green line is from observations. All these other lines are from models. These are different RCP scenarios. That's concentration of greenhouse gases. This is from the 5th Intergovernmental Panel Report on Climate Change. And the point I want to make, which is generally well received, although there may be dissenting views, that the climate models don't do a terribly good job of predicting the rate of Arctic sea ice decline. I want to be a bit careful here. The reason they don't do that could be for many reasons. Natural variability is a big part of it. Okay, so there's chaos in the system. Climate models do demonstrate natural variability. This is the sea ice extent that we're looking at here, and sea ice is just a very thin layer sandwiched between a very huge atmosphere and a very huge ocean. Okay, small imbalances of those heat and mass fluxes can have a massive impact on the sea ice extent and sea ice coverage. So it's largely due to inaccurate simulation of the atmosphere and ocean. However, the parameters inside sea ice models, some of them have quite a lot of uncertainty associated with them, and the representations of physical processes can be uncertain. And that level of uncertainty can have a big impact on the sea ice simulation, not the climate simulation, but the sea ice simulation. So thickness and extent can be varied by a huge factor according to what parameter choices you use and what physics choices you use. So modelling sea ice in climate models. So climate model representations of sea ice comprise continuum local balance equations of heat, mass, and momentum. I think Elizabeth mentioned 90 conservation equations or something like that yesterday. We had some discussion last night about that. Okay. I just threw a few up on my blackboard in my office. Okay. This is the momentum balance of sea ice. This is a reduced form of the Reiner-Rivlin constitutive law. And for those of you in the know, these are the muscular equations. Okay. So I think Chris said sea ice comprises sea ice flows, right? Sea ice is a muscular. Remember that. Okay. I think I published a paper a few years ago on that topic. So sea ice in climate models are continuum balance equations. But those balance equations contain parameterizations or representations of physical processes. And these are in the sea ice literature, and I understand this is a bit different from the general mathematics literature, are often divided into dynamic and thermodynamic processes. Dynamic processes comprise such things as pressure ridging and deformation. So this is a satellite image from Ron Kwok. This is a numerical simulation from Mark Hopkins. So air drag, ocean drag, breakup of the ice, wave-ice interaction will fall into this sort of category. Then there are thermodynamic processes. So these are a couple of things, such things as melt ponds, which have an impact on the albedo, I'm given to understand. And this is sea ice growing in a laboratory experiment. You can probably see these streamers here. That's brine being released through those streamers. Okay. So there are many physical processes which are represented in climate models. And that demarcation between dynamic and thermodynamic processes is a little artificial in some cases. This is an example of a situation where they combine. This is the formation of a sea ice lead, crack in the ice cover. Okay, so the lead has formed mechanical divergence in this case, but it's a source of rapid sea ice growth in the winter because you form a crack in the ice cover, you're exposed in the warm ocean at minus 1.8 degrees, okay, to the cold air at minus 30 degrees, and you have rapid ice growth. So there are connections between them. And I'll talk about that a bit later on. So these processes cannot be incorporated in all their fine detail. So they are parameterized, that's simplified mathematical representations of the salient physical processes which are relevant to the large-scale concerns of client models and whatever they may be used for. But also those parameterizations have to fit within the technical constraints of these large-scale models. So you can't have 20 equations describing frazzle ice growth in sea ice, or you can, but don't expect to get to a client model. Okay? So you need to, the model representation has to be economic in some sense. So that's what sea ice models are, and a flavour of some of the parameterizations or processes that are represented. So I just want to say a few more words about the need for parameterizations, because this is not necessarily obvious to a fluid dynamicist. So models show that inadequate sea ice simulation can be caused by uncertain boundary forcing, okay, so the air in the ocean of course, but also by uncertain sea ice model physics. So if the albedo is wrong by a factor of 2, your sea ice is going to be badly wrong. So for the boundary forcing, increasing the resolution of the atmosphere in the ocean in numerical models will hopefully result in more realistic forcing of the sea ice cover. So that is definitely needed. That more realistic forcing will result in more realistic sea ice simulation. If we don't have the winds driving the ice, we can't predict how the ice moves. By contrast, for a given boundary forcing, increasing the resolution of the sea ice model itself is not really expected to have a material impact on the behaviour if you're solving the equations properly. Here's an example where the atmospheric and oceanic forcing is kept at a constant resolution and it's driving a standalone sea ice model. So the sea ice model is passively responding to air and ocean forcing. This is a 1 degree resolution sea ice model. This is a 1/4 degree sea ice model resolution. So what we're not seeing is lots of little turbulent squiggles, okay, or lots of new processes you might expect in a numerical simulation of the atmosphere or the ocean. This is because the inertial term is generally pretty small in sea ice models. So to get a better description of sea ice, we need to include realistic parameterizations that account for the physics, because cranking up the resolution itself is not going to solve the problem. We need to have representation of the subgrid scale physics. And this is really the cottage industry I've been working in for the last 15 years or so, maybe longer. Let's not go there. Okay. So this is my talk structure. So we've already done the description of sea ice models. Now I want to talk about 3 different parameterizations that have been developed in my group. There are several others. In particular, melt ponds is the most prominent, but Daniela Flocco is talking later this week on melt ponds, so she can give you the skinny or the down low on what melt ponds have to say for climate models. So form drag, rheology, and frazzle and grease ice. Form drag. That's a pressure ridge. So here is the vertically integrated, i.e. horizontal momentum balance that appears in sea ice climate models. Okay, this is essentially F equals ma. The terms that have been highlighted in pink are the terms which are largest, okay, of order 0.1 newton per meter squared. So that's air drag, ocean drag, and ice interaction force given by the rheology of the ice cover. So I particularly want to focus upon the air drag and the ocean drag terms here. So form drag over sea ice. This is the wind blowing over the ice and the ice dragging the ocean, typically. So the drag laws that appear in sea ice models take this form. The shear drag is proportional to the velocity of the air above the ice squared, or the ocean beneath the ice squared, where you have some drag coefficient. So this form for the drag law is true whether the drag is skin drag, either from surface roughness, or it's from form drag, so mechanical blocking of the flow of the air in the ocean. So that's fine, that's convenient. Okay. The problem is that climate models have to use the same drag coefficient regardless of whether the sea ice cover looks more like this, flat, or more like this, ridged. And so to alleviate that, we developed a model which explicitly accounts for form drag. So the prominences of the roughness, or the large-scale roughness features of the sea ice, so the pressure ridges and the kills. So it ain't rocket science. The air drag coefficients and the ocean drag coefficients are the sum of various terms accounting for these topographical features. So you still have the skin drag terms in here. You've also got features corresponding to the pressure ridges, the pond edges, the edges of the flows, the keels. All of these deformations of the ice cover have a significant impact on the total drag coefficient. And the geometry of the sea ice is something which is not inside climate models. So this has to be parameterized. And this is parameterized based upon empirical statistics of the deformation features, but also, luckily for us in SICE, one of the many traces Elizabeth mentioned is the deformed ice fraction. So in our particular model, we use that deformed ice fraction and some empirical parameterizations, or really curve fitting really, to get some idea of what the geometry of the ice cover looks like. Yes, so the drag coefficients are generally proportional to the amplitude of the feature divided by their separation with some sheltering function, which accounts for the wake behind the features. So more recently, we've extended this to include internal wave drag. So in particular, when you have keels on the bottom of the sea ice pushing into the ocean mix layer, or even projecting from the mix layer into the ocean beneath that, you generate internal waves, and those internal waves can carry momentum away. This is based on the theory of Mars-McPhee, and I won't say any more about that because there's a poster on this by Daniela Focco later this week. So incorporating form drag has a significant impact on the total drag coefficient. So here we're looking at the total drag at the air ice interface and the ocean ice interface. This is for September. This is a climatology 1990 to 2007. So the first thing we notice is that the drag is not constant. Okay? So in existing climate models, that would be one number, but actually it varies by a factor of 4. So that ain't terribly good. So you want to incorporate this into models. We can see that a large part of that is due to the pressure ridges and the keels, which is what you'd expect. Those are the biggest features. But also, the flow edges play quite a prominent role. Okay? So the freeboard of the ice above the ocean, or the draft of the ice beneath the ocean, they provide a bluff surface against which the wind and the air flows encounter, and that creates an enhanced drag. So this has quite a significant impact on the... Sorry?
Say very simply how that data is obtained.
That's a model output. The drag coefficients based on the very limited measurements over particular features. Okay? And then quite a lot of extension to get there. Incorporating this spatial variability, and I should also point out there's a great deal of temporal variability in the drag coefficients as well, okay, has quite a significant impact on the sea ice simulations. So this is September again in the Arctic, ice concentration, thickness, and motion. This is the climatological impact, okay, and we see that we have generally quite a bit of lower ice concentration and thickness when we incorporate this representation of form drag. Now this is actually mainly because those form drag features enhance the transfers of heat as well as momentum. Okay, so when you take account of the keels, right, dragging through the ocean, that mixes up the ocean and gives rise to enhanced oceanic heat flux, which tends to melt them more. So here are particular years, so September 96 and 2007. And the main feature here is just to demonstrate that the impact of including form drag varies from year to year. Okay, so it adds to the internal variability in sea ice models. These particular years have been chosen because this is a year of high sea ice extent, and 2007 was a year of very low sea ice extent. So this is an example of a particular parameterization, in this case form drag, which has significant impact on the simulations and introduces additional spatial and temporal variability. We're extending this work as well, pretty much, well, I would say as we're speaking, but Daniela is probably in the audience. Okay, and we're also looking at new topography data to better characterize the geometry of the ice-ocean interface and also the ice-atmosphere interface from IceBridge. So I'm going to skip on because there are two more parameterizations I want to get to. Anisotropy. So this is the momentum balance I showed you earlier. Okay. Now I want to focus a bit upon the internal ice stress term. So the internal ice stress term results from ice interactions. So this is the stress related to rupture of the ice, frictional sliding flows past each other, pressure ridging, collisions between the sea ice flows. So the representation of rheology in sea ice models has been an ongoing struggle, shall we say, for the last 30, 40 years, possibly longer. But in particular, the internal ice stresses depend upon the nature of the ice cover and the fact that it is observed to be anisotropic. So here are some images from various different length scales. That's the whole basin scale. You can see the 100-kilometer scale there. That's a zoomed-in region there. That's 15 kilometers down there. Okay, and this is a laboratory specimen. Okay. So what you can see is that there are features in the ice cover, all these scales, which are regions of weakness. So hopefully I'm not fobbing you off too much if I draw these red lines to indicate here are some of the lines of weakness. So on these optical images in Landsat here, you can see here, the dark regions are regions of either open water or thin ice. So they tend to be weaker than the surrounding ice because there's no water, no ice there. Okay, so the ice cover is anisotropic, we see that, so what? Well, suppose that red box is a notional grid cell in a climate model. Consider the forces required to squeeze it in this direction or orthogonal to that. Okay? So in this direction you've got to squeeze open water or thin ice, requires much less force than to squeeze it along the thick ice features. Okay? So the ratio of these forces could be up to a factor of 10. So accounting for these oriented weaknesses has a material impact on the momentum balance. It has a material impact on the sea ice stress term. So for that reason, we have accounted for the observed anisotropy in the momentum balance of sea ice through altering the sea ice stress term. In particular, we've developed what's called the elastic anisotropic model. Okay, but the elasticity here is artificial elasticity. It's the elasticity of the EBP model that Elizabeth mentioned yesterday. Okay, so this anisotropic model, in particular, has to describe the observed anisotropy and how it changes with time, and relate the sea ice stresses to that anisotropy. So this is to motivate that the sea ice actually comprises a collection of diamond-shaped flow aggregates. Okay, so maybe a hard case to make in some cases, but this is ESA imagery of shear features, and you can see the regions of high shear essentially are forming lines like this, coulombic lines. And this is the output of a elastic, plastic, discrete element model, okay, where there's no anisotropy imposed at any scale, but anisotropy emerges. We see these emergent damage zones, okay, which tend to form roughly diamond-shaped features. So our starting point for this simple model is that the ice cover comprises a collection of diamond-shaped flow aggregates. Okay, hope. Okay, a bit of a technical failure here, it's not advancing. Here we are. Okay. So this is a notional grid cell of our model. So we assert that the ice cover comprises these diamonds, and we account for the orientation of those diamonds with what's called a structure tensor, okay, which essentially takes the form of a 2x2 matrix. So it's unity if it's randomly oriented, modulo a half, or it takes extreme values if the diamonds are aligned in particular directions. we account for the evolution of the orientation through an evolution equation for the anisotropy tensor, the structure tensor. So broadly speaking, we have thermodynamic processes which tend to make the ice more isotropic, and mechanical processes which tend to make the ice cover more anisotropic. So the thermodynamic processes include things such as the flows melting apart, which doesn't know about orientations. They tend to fall apart isotropically, or the flows freezing together. And we've done some recent work on characterizing this thermal rate of return to isotropy. The fracture term accounts for failure of the ice cover, either to form conjugate Coulombic cracks in biaxial compression or axial faults, ridges. So if you compress biaxially, you tend to form these Coulombic faults. If you compress just from one direction, the ice tends to pile up to form those pressure ridges I showed you earlier. In either case, this introduces anisotropy, which is accounted for through this U orientation S. So that tells you how the anisotropy evolves over time, but we want to relate the sea ice stress to the anisotropy. And this is a tricky business, and I'm just going to skate over some of the details here. But what we can do is we can look at the edge tractions on these diamond-shaped regions. So red and yellow, okay, are here. So these are the tractions on the red and yellow lines. The Heaviside functions activate the pressure ridging force, Fr, or the sliding force, Fs, if the flows are moving into each other. If the flows are moving apart, there's no force. So this enables us to work up the tractions along the edges of the flows. If we consider an ensemble of these flow regions, like so, we have the edge traction along the edges of the diamonds, along this line, and using the mean stress theorem, we can compute the edge traction along an arbitrary orientation. Okay? So then that traction there is given by this term, so we're relating that traction to the edge tractions. But in particular, that traction along the arbitrary line is also given by the inner product of the normal of that line with the sea ice stress. So this is the starting point of backing out the sea ice stress from this process. So another 10, 20 pages of algebra, well, let's say 10 pages of algebra, and you can get this sea ice stress. So those are the basic ingredients of the theory. So this has now been stuck into the sea ice model, and here's a snapshot of the simulation output, October 1990. Here. So the first thing to notice is that it's mainly red, and here red means anisotropic. So our simulation does show that the ice cover is mainly anisotropic. It also varies. This degree of anisotropy varies quite rapidly on the wind pattern timescale, because the wind is primarily what causes the ice to crack, and I'll show you that in a moment. The other thing to note is that this is notionally shear stress versus compressive stress. So those of you in the know will know this black ellipse here is what's called the elliptical yield curve. It's famous from Bill Hibbler's model. Okay? But what we tend to find in our model is that the shear stresses tend to be significantly greater than one would predict given an isotropic plastic rheology of that nature. So anisotropy is present pretty much all the time, evolves rapidly, and it makes the ice harder to shear. So here we see some simulations. On the top row shows shear strain and divergent strain. The bottom row shows shear stress and the divergence of the stress. So this is a 10-day animation here. The diamonds in the background show the degree of anisotropy. So it's pretty much always anisotropic. And these features we're seeing here, they're emergent deformation features. They're not imposed in the model. They come out of the simulation. So they evolve quite rapidly. The anisotropy evolves rapidly. So this paper, which has been submitted, demonstrates many of the interesting features of the anisotropic model. In particular, Harry Horton is giving a talk on this on Friday, so I'll let him go into more detail about that. So this difference plot here, so this shows an isotropic rheology model for thickness and ice motion. this shows the difference when you include anisotropy. So what we tend to find in this simulation, okay, this is a September average, is that the ice is thicker with anisotropy than without. And the main reason for this is because the ice shears more slowly, and so there's greater time for pressure ridging to pile up the ice against the Canadian archipelago. But I stress this is a feature of this particular simulation. Okay, other simulations may show different things. That's partly what our paper is about. So just to summarise that then briefly. So observations show the ice cup is anisotropic. We took the bull by the horn, included anisotropy directly into a sea ice climate model. It affects the mass and flow to leading order, okay, and particularly accounts for a range of different mechanical processes or responses, which in the past has not been able to simulate. People have taken the plastic yield curve and they've varied it in various ways. That sort of comes out of our simulation because the effective sea ice yield curve, which is actually a yield surface, evolves with time. Okay, the assessment on climate sea ice simulations is ongoing, and this is something we're working on now. Okay, so now I want to talk about something completely different, so to speak. So frazzle and grease ice. This is some recent work we've been doing. So I mentioned at the beginning of the talk that leads form in the ice cover. Generally, due to mechanical stresses, you have a lead forming like so. In the winter, this is a source of rapid heat loss from the ocean to the atmosphere. Okay? The leads may only comprise 1 or 2% of the ice surface, but there's a very large heat flux from the leads to the atmosphere of circa 300 to 500 watts per meter squared. So that's seriously high. Okay? Of course, that means that the leads quickly freeze over. So the leads in the winter are also a great source of new ice formation and also brine release to the ocean. Because when you freeze seawater, you release brine. So how do climate models account for new ice in leads? So you have a break in the ice cover. You lose heat to the atmosphere like so. And you generate enough ice to account for that heat loss. Okay? So you take the amount of heat loss, you instantaneously create some ice to account for that heat loss. Okay? So that's the latent heat is what's causing the ice loss. And then that ice is then bunged into a thickness class, okay, which several people have mentioned already. The default is a very thin thickness class, which seems reasonably logical, of 5 centimeters. So that's kind of how the standard approach of dealing with it. And I mean, that has some nice features, but also has some issues. In particular, it doesn't account for the actual process of how the ice forms. So when a lead is exposed to the atmosphere all of a sudden, the ocean gets very cool, it becomes super cooled, and tiny crystals of ice called frazzle ice form. Okay? During this process, the temperature will generally drop. So unfortunately, can you see this? There's supposed to be a blue band here when the lead is forming. You can see the temperature drops, it becomes super cooled. As the ice forms, the frazzle ice forms, salt is released into the mixed layer, okay, and so it becomes very salty. So a lead forms, the ocean mixed layer beneath the lead becomes supercooled very rapidly. Tiny crystals of ice form called frazzle, okay. They release salt, and those frazzle crystals, they're buoyant, so they float to the surface. And when they float to the surface, they accumulate at the ice surface. What happens is that the wind tends to blow those frazzle crystals to one side of the lead, okay, to pile up, to form what's called grease ice. So these are the processes which are currently missing from climate models. So how have we tried to deal with this? Well, we've considered the balance equations for ice concentration, temperature and salt in the region of the ocean mixed layer beneath the lead, in the surrounding mixed layer. We've also accounted for the fact that when frazzle crystals form, they tend to pile up to form a grease ice coverage. So just a few words about modelling those processes. So here are the, assuming the lead box is well mixed, we have ODEs describing the concentration of crystals, salt and heat in the lead box. Firstly, we have a heat loss, so Q is generally negative. This is the heat loss to the atmosphere, okay? That cools down the water, resulting in ice formation. So when the ice forms, it releases latent heat. You also have to turn the water which forms an ice crystal from its current temperature up to freezing temperature. When you form that ice, the number of crystals go up, and also you release salt. Crucially, these fragile crystals are piled up in a grease ice layer. And we also account for advection of the crystals from the lead box into the surrounding area. When the fragile crystals are advected beneath the surrounding sea ice, they precipitate onto the other side of the sea ice model. This is the grease ice representation. So the grease ice piles up to form a profile like so, which is a balance between the wind drag force and the mechanical resistance force, which is proportional to the buoyancy of the ice, giving rise to this shape here. So here are two scenarios where the lead is very wide or very narrow. So, okay, that's great. So we can solve those equations, not quite analytically, but not too hard to solve either. Okay. The trouble is we want to put this in a client model, and we cannot represent hundreds, thousands of leads in the client model. What we can do, however, is calculate the lead box temperature and the ambient box temperature from the heat fluxes and the changing ice concentration. And we don't solve the balance equations inside each lead. We simply assert that the lead is either in steady state or it's cooling down. Okay? From that, because when it's cooling down or when it's in steady state it has a particular temperature, from the mean lead temperature it's possible to back out what the fraction of leads producing fragile ice is. So from the temperatures in the lead box and the ambient box in the mixed layer, we can calculate what the total ice production rate is. So we calculate the rate of production of ice. So here are some simulations showing the impact of this new model. So again, this model has been coded up into SICE. Here shows some simulations from 1979 to 2014. So Antarctica and the Arctic. So this is showing the ice formation rate. This is a fragile ice formation rate, and we're comparing the solid line, which is the new super duper model, with the dashed line, which is the old Rofi model. I'm sure Liz will mind saying that. Okay. So solid versus dashed. So we find a dramatically enhanced rate of fragile ice formation when we account for this process. The amount of congelation ice, that's regular ice formation, is similar, okay, whether we include the model or not. Okay, there is a difference. The total impact on the amount of ice is relatively small, but not negligible. Incorporating fragile ice in this way can have a half-meter impact on the ice thickness in the Arctic or the Antarctic. Okay, so why does incorporating this fragile make a difference? So fragile ice tends to happen in small areas over a small period of time. So the left-hand side is going to show the new scheme. The right-hand side is going to show the old scheme around Antarctica. This is a cartoon, okay, not actual model output. So here is a region of high wind speed. Okay, in both the new scheme and the old scheme, it's the same. It's imposed. We have ice opening in both the old scheme and the new scheme. Okay, that has not been affected by the fragile model. So in the old scheme, we immediately have very rapid rates of ice production. In the new scheme, that's not so. The water in the leads is cooling down. Okay, there's a delay before fragile ice can form. So this is the fragile formation rate now. So we have lots of ice forming in the old scheme. It's only forming very slowly in the new scheme. So a day later, we see the ice production rate decreasing significantly in the old scheme, but it's just starting to kick in the new scheme. So now the ocean's got supercooled and frazzle crystals starting to form in earnest in the new scheme, whereas most of the ice has already been produced in the old scheme. So the leads are starting to close in the old scheme. Okay, they're still open in the new scheme, and partly this is because when the frazzle crystals precipitate to the surface and push against the edges by the wind, they keep the lead open for longer. Okay, if all these crystals being piled up against one side, that means for a longer period there's open ocean in the leads. So we continue to get new ice formation in the new scheme. So incorporating this new physics affects both the timing and also the magnitude of the ice being produced. Okay, so Arctic versus Antarctic. So Antarctic has got a big marginal ice zone, and frazzle and grease ice tends to be focused in the marginal ice zone. Okay, so here is a simulation showing the rate of frazzle ice production per unit area of ice for the Antarctic in dashed and the Arctic in solid line. So you have similar amounts of congelation ice growth in both the Arctic and Antarctic, but you have historically found to be much more frazzle ice formation in the Southern Ocean than in the Arctic. This is also backed up from field observations. Okay, and this is largely down to the fact there's a much wider region of open water, marginal ice zone in the Southern Ocean. That's still true, but over recent years, the MIZ has got bigger in the Arctic, and the rate of frazzle ice production has got greater in the Arctic. So these models of frazzle ice formation is definitely important in the Southern Ocean right now. Okay, it is going to probably become much more significant in the Arctic as time goes on. So just summarize those points then. So a new frazzle and grease ice model has been developed, incorporated yet again into our favourite community sea ice model, SICE. Okay. The main feature is that the ocean beneath the lead supercools before frazzle ice starts to form. The frazzle ice is herded as grease ice, and because it's herded as grease ice, this has the impact of keeping the leads open for longer, so more ice is formed. In particular, it's worth noting that in the central pack, where you have leads only occupying a small fraction of the surface, you have much more frazzle ice formed in the new model than in the old model. And that's actually the original motivation for doing this work in the first place. We were interested in dense water formation in the Southern Ocean. Okay, so I've rattled through 3 parameterizations. There are several others that my group has developed, but the purpose of this is to show how we're trying to capture the important aspects of the physics in a simplified way that can then be parameterized into climate models. Whether those models are actually used to predict climate or for other purposes. I think Elizabeth showed yesterday there are a whole range of different uses for these models nowadays. So just to summarize them, I will go back to agreeing, admitting, okay, enjoying a sense of camaraderie with people to acknowledge the fact that atmospheric and oceanic boundary forcing is of course vital to sea ice model simulation. But I would contend, and I think I have evidence for this, okay, that adequate representation of uncertain sea ice processes is also necessary to represent sea ice adequately. Parameterizations help to capture some of these main features. They have a leading impact on sea ice simulations in standalone sea ice models and in sea ice ocean models. Okay, this can be demonstrated. Interpreting that in climate model context is a bit harder because it's pretty hard to interpret climate model output. And not shown here, but in a talk later on in the week by Daniela Flocco, incorporation of parameterizations has led to material improvements in predictive skill of seasonal sea ice extent. And I'll leave with the anodyne, and benign conclusion that inclusion of pseudo parameterizations into the next generation of climate models may make them better.
We have several minutes for questions. Danny, do you want to just select?
Sure. Okay. Yes, Chris.
So given that sea ice is not comprised of diamonds, how do you hope to actually evaluate whether the anisotropy tensor is realistic from observation?
Well, sea ice, okay, I don't necessarily agree with that first statement. Okay, so sea ice is comprised of diamonds where the sea ice stresses are important. Okay, where the sea ice stresses are unimportant, they're not. Okay, so in the central pattern winter, the fracture patterns do look like you're demarcating roughly diamond-shaped regions, and that's really when the sea ice stress assumes its greater significance. So what's the second part of the question?
How do you hope to? You have an evolution equation for your anisotropy tensor.
Mm-hmm.
How do you expect to constrain that from observation?
With observations of the fractures in the ice cover.
Yeah.
Okay, so that is work which is ongoing. It's pretty difficult because but it's maybe possible. Part of the issue is knowing what the coincident forcing is, as well as the features. You can see these features, okay, and it's observed they have an orientation that suggests this diamond structure, okay, underlying coulombic in-plane failure. Relating to that, the surface forcing is a harder problem. So it's not impossible, but it's tricky, and it is ongoing.
Have you considered using SAR observations of deformation or
Yes,
shear,
that's exactly what we are doing.
scaling laws? Have you done that with the EAP model?
We've done all of that with the AP model. Yes, that's what we're currently doing, is looking at SAR data. Okay, regarding scaling laws, well, okay, there's a certain segment of the CIS community is really interested in scaling laws. Okay,
Which one?
so yes, we have looked at scaling laws. Okay, and for what it is worth, we also regain a power law distribution of CIS deformation. Okay, from the elastic anisotropic plastic model. Okay, when we consider a range of different types of deformation. And that should be shown in Harry's talk on Friday. I think, Gray, did you have a question?
Well, it's a question about the frazzle thing, which we might have to pick up later, but can I just understand briefly? You had accumulating grease ice,
Yeah.
and so you had a calculated thickness of that. Was
Yeah.
that greater than the 5 centimetres that was assumed?
Yes. Yes. Sorry, that was
So
the.
that's part of it.
Yes. Well, that's not only part. That's the crucial aspect of it.
Okay, I was wondering if you were also throwing some of the ice underneath the existing
Yes, we do.
ice.
Yeah. So I maybe should emphasise that more. So yes, the point is that the grease ice is considerably thicker than 5 centimetres.
Right.
And yes, of course, we do account for the volume of ice that's been piled up, and sometimes it overrides the ice to form piles on the top or the bottom.
And then finally, you had this delay because you're sustaining supercooled water.
Yes.
Did that incorporate a nucleation delay, or was that all just a growth delay? In other
It's
words,
largely growth.
so it's just that you've got a growth of frazzle proportional to supercooling, or
And the number of crystals that are there.
okay.
Ken?
Since you're in search of fidelity,
Yes.
I've been struck by, it's not something different than you've been speaking about, but up in the Arctic, how dirty I've noticed the ice to be and how extensive that dirtiness sediment bringing up from brine rejection, from storms, and so on. And I was just curious if that's been thought of, or if it's been, incorporated, or
Well, okay, my group has not not tried to model it. We are aware of that. We have done sensitivity studies where we effectively alter the optical properties, assuming that there's some dirt
Right.
there.
Yeah.
Okay, but we've not modelled like alka or anything like that.
My group is working on it.
okay. All right, there you go.
To stay on time, we'll probably need to leave it right there, okay?
Yeah, just
However,
Maybe while Lisa's coming up, you can ask your question.
okay.
I'll start to put my laptop away. Go on.
My question was on the phased parametrization.